please take it away. Should I do it again?
Yes, please.
Okay. Deepak, how do you pronounce your last name? Is it Pathak?
Yes.
Okay, it is my pleasure to introduce Deepak Pathak. He's one of our new faculty members. The truth is, here is someone who needs no introduction. So Deepak, please take it away.
Thank you, Howie, for the last minute impromptu introduction. And so before I start my talk, let me mention one thing that, so as Howie mentioned, I began here this August, and I gave my job talk in last year spring. So, and since then I have given quite a few talks at CMU, so you might have seen a bunch of the content, but I promise that in today's talk, there is something new for everyone, even if you have seen all the past talks. And the first half might be what you have seen, but as we go towards more to the talk, I'll show more and more new content, which is freshly out of the oven and is not even public yet, much of that stuff. Okay, so today's talk, I'll try to pitch in some ideas that I've been thinking about in with the goal of improving generalization in machine learning, and with application to primarily robotics, but computer vision, etc. So much of the motivation that guides my research is basically inspired by humans as to how well can we generalize to unseen things that we have not been trained on. And this generalization is basically makes us who we are. It's the essence of human intelligence. Let us see where we are with machine intelligence. So today we have these systems which can play this complex game of Go, translate speech, recognize language, and maybe we can have cars that can drive themselves not too far into the future. But unlike humans, these systems are not that intelligent. In contrast, these systems are specific to what they are trained for. Like for instance, we have a completely different system that plays a game of Go than the one that drives a car. And there is no generalization across these tasks, while as humans, we can do all of these things. Maybe it's a bit too far out an example to ask for an algorithm to play Go or drive a car simultaneously. So let me give you an example which is closer to home, that of supervised learning. The most basic thing we study in machine learning. Let's take task of image classification, where the goal is given this image is to output the class label. The way we train this is by showing these models a lot of these images, which come from a big data set, which has training and test accuracy. Now, we have really excelled this problem, at least in the machine learning or deep learning community, so as we like to believe. And the performance on these data sets is superhuman, like really well. But let us see, even the best of these models, how well do they generalize? So when I take this model and when I apply it on a random video from YouTube, this model completely fails to generalize. Like this, it finds things like cobra snake, ray fish, flatworm, and this result is not a toy result. I'm using one of the best models available out there for this kind of task, and this is completely failing in the real world examples, and the accuracy drops to very low. So why is it the case? Well, if you ask a machine learning person, the answer will be that it's not very surprising because the data that it is trained on contain dog at the center of image in good condition, good lighting, good pose. All these conditions don't hold in the real world. And in fact, that is the problem I would like to argue, that in all of our learning based methods, we start with this fundamental assumption that our training data and our test data basically comes from same distribution. But in real world, this assumption gets violated all the time. And whenever that happens, our algorithms fail to generalize. So much of our focus in this talk is how can we build algorithms that can actually adapt in the real world without failing to generalize. And this problem, I would say, is even more severe in robotics, where we have all these robots that can do all these crazy Parker skills, but transferring these skills to a merely simple task of putting a box on the table is still in many ways an unsolved problem. And the reason is that Our real world is continuously changing, and we want to deploy these words in the real robot. And this generalization is very hard to obtain. So in today's talk, I'll focus on how can we bridge this gap and generalize beyond what the agents are trained on. So before I go into the methods, let me give you an example. So let's say the task over here in this case is to tie a knot. So here is a robot, and it sees this image. So input is image. The goal is this image, and the idea is we want a policy that can output the series of actions to tie this knot. Now it's a very straightforward task: input, output, and actions. Right? Now, how do we solve this today in robotics or in learning in any domain? The most common approach, or I would say the most successful one, is this imitation learning, where human comes and controls the robot manually and try to solve the task. And by doing this, we collect data for the robot, which is really all the torque and joint angles. Now, as you can see, this is very tedious for the expert, but the main problem is this has to be repeated for every new task we might want the robot to do. So this is not very scalable approach. Hence, people have also been focusing in the last several years on this approach called reinforcement learning. And what is this approach? The high-level idea is as follows, that unlike requiring experts for a task, we let the policy or the method discover how to solve the task itself. So given the input image, there is a policy which takes a series of actions that goes to goal image. Now, the way this policy is trained is by giving a reward whenever a goal is achieved. So you give a high reward, and the policy is trained to maximize this reward. But if you think about this, the policy in the beginning starts being random because there is no expert. Now, in this scenario, if the policy starts being random, how likely is it the case that a robot will even end up tying a knot just by randomly acting? Well, it's really, really unlikely. In fact, by some of my estimate, in this setup, it will take these many interactions to tie the knot even once, which is completely inefficient and completely impractical to deploy it on a robot. So why is there so much craze about reinforcement learning in the community, at least in the machine learning community for the past several years? Well, it's because of these results that you might have seen. However, the story here is not as glorious as we study about reinforcement learning, because in these scenarios where people are able to train these agents that can just function by looking at the game screen and press keyboard buttons to play the game, they do not rely on the sparse reward, but they rely on score of the game as a reward signal that basically guides the agent at almost every time step. So this provides a very dense reward, which is almost every step of the trajectory. And in some ways, it's much harder than an expert in several settings. Like even in tasks like navigation, where the goal is to reach some target location, many approaches shape the reward function by giving these apples in between. The goal is to reach some location, but these apples are given just to guide the agent so that it doesn't get completely lost in finding the goal. But in real world, there is no apples. In real world, the reward could be delayed by days, months, or year, such that it's hard to propagate back to where you are. So how does this child over here know? How should she act to become pilot 20 years later? Like, does she optimize any reward and backprop all the way to her childhood? Well, not quite. So this is where developmental psychologists like Alison Gopnik, Laura Schultz, they argue that human babies, in particular in the early days of childhood, are not even driven by any end goal of any sort. They are completely driven by their own intrinsic notion of what they want to do in the world or what they want to achieve. So they are guided by something known as intrinsic motivation or curiosity. For instance, this kid is playing with Legos, not trying to optimize to get a PhD at CMU 20 years later, right? It's just playing with the Legos, having fun, and that's it. And in fact, this kind of behavior is not just about humans. This is seen in every biologically intelligent species. For instance, here is an example of a crow and a chicken. So on the right, these are New Caledonian crows, which are one of the smartest birds on the planet. In fact, they are so smart that they can pick up food from a test tube by folding a wire. And these birds are known to have a very long childhood, like almost 2 years of childhood, where they explore without goals. On the other hand, these chickens are one of the dumbest animals on the planet. All they do is peck for grains and nothing else. and they have almost no childhood at all. They start pecking for grains from day one when they're born. And in fact, this stark correlation is seen across several species. So on the x-axis, there is weaning time, which is length of childhood, where they explore without goals. And on the y-axis, there is some notion of how intelligent the species is. And you can see there is a good correlation across several primate species as to how intelligent they are and how much time is spent in childhood without goals. So this leads to one of our conjecture is that maybe by not giving goal to the agent, you are making it not overfit to the task. Hence, they are able to generalize better in the real world when deployed later. So this is one of the key insights which we have taken inspiration from in the past and proposed some models. So I'll briefly cover this in the very quickly, and then I'll go into more details as to how to scale it to real world. Now, if you want to implement this conjecture in computers or really implement it as an algorithm on a robot, the first question is, what do you even do if you do not have any goal or any task to solve? Can we somehow implement this notion of goal-free exploration, curiosity, intrinsic motivation in the agents? Well, people have been driven by this question for several decades at this point in the machine learning community. However, most of these prior approaches have always focused on in trying to encourage exploration in the context of some end goal. But what we are interested in is trying to build algorithms that can explore without any goal given at training time. And by goal here, I basically mean extrinsic goal. So agent can still have their own goal or their own task, but there is no external task that you are forcing it to solve at training time. So I'll not go into how do we propose this model, but I'll just give a very high level idea as to what does it look like. So we have proposed this called something known as computational model of curiosity. Like it's not, I'm putting curiosity in quotes because it's just used as a guiding term. I'm not talking about human curiosity or animal curiosity. What I'm talking about is this notion where an agent is dropped in a new environment and it can learn to explore and gain as much useful information as possible completely by itself without requiring any expert or any human to guide it. So what's the general idea? General idea is really, really simple. So in the beginning, when the agent is dropped in an environment, it just goes around and acts randomly in the very beginning. And it collects some data. So from that data, it trains a model of how the world works. So if I am here, if I do this, what will happen next? Okay. Then we use this model to make predictions about the consequences of agent's action. Like what if I push this mouse from this position to the right? Well, it will fall off the table. Now, can I predict this? So whenever the agent's prediction does not match with actually what happens in reality, we say that agent has become more curious and we allow it to explore further and go back to the same scenario and collect more data. And here is the key part. As the agent goes back, gets more curious, collects more data, its model becomes better. And as its model becomes better, its error will become low and it will no longer be curious anymore. And then it has to find something else to be curious about. So just by this notion of being curious and trying to find things which your model cannot explain. So it's basically trying to seek explainability, like try to do things which allow you to explain what is happening in the world and try to find those scenarios. So this basically allows the agent to learn continually on its own and discover new things in the environment. And we have, so this is, we began this work at least 4 years ago at this point, 3-4 years ago. And we have shown that this kind of idea can be applied across a large variety of environments. In fact, we have shown results on almost all the environments that people show results with deep reinforcement learning. But we made one change that we did not use any rewards at all. And then agent can learn to navigate, it can learn to walk, it can learn to play all these games without using any score from the environment and it can solve this subcontinuous control task as well. But in today's talk, I want to talk about how can we take these ideas from the simulation to real world setups. Because simulations and games do not capture, no matter how fun they are, they do not capture the ultimate utility of any of these approaches just by themselves. So in this talk, I talk about how can we scale these ideas of curiosity-driven learning or learning without any external goal at training time to real robotic scenarios. And let me, before I go into all the ideas, let me try to summarize what do I think are the key things which are missing from this literature so far that are prohibiting it from being applicable to real world. So the first immediate point that anyone who has seen these games, this is their first criticism. Like, how do you learn efficiently in the real world? Because in games, in simulation, you can take as many steps as you would like and nobody cares. But to function in the real world, we really want these algorithms to be really, really simple, efficient. Second question is, when we apply these algorithms to simulation or games, the action space of these agents is basically like keyboard, a discrete button, like go left, go right, shoot a bullet, or pick up something. But in real world, if you're trying to apply to robots, this action space really matters a lot. Do you act in the torque space, joint angle space, and can you do dynamic tasks, things like that? Now, third thing is that if you really want this learning to go on in the real world forever, like if you really want to solve this problem of generalization beyond training by actually adapting in real time continually over the case, you have to make these algorithms applicable generally to more robots and not just your robot in the lab. So it should generalize across robots, across hardware, just like the story which we have in computer vision, for instance. Like we train a model on ImageNet, and then we fine tune it on multiple data set, multiple tasks over time. And there are several other directions which I'll cover briefly as part of the ongoing attempts, like perception, action, planning, sim to real, etc. So let's take a deep dive in each of these ideas in scaling these curiosity-driven methods to real world. So the first question is about efficiency. Now, before I try to solve this efficiency problem, let us say, what if we just try to transfer the same algorithm that is applied on the video game settings in order to explore the environments and learn to play the game without reward directly on the robots? So here is one of our attempts where we took just the same algorithm, which is performing this curiosity-driven learning by building a model and then acting to find examples that can violate the model. Now, if you look over here, it just does something very stupid. It just hits the objects. Maybe you can say it's being curious, but it's not being usefully curious in any way. So this is a failure example. In fact, it did not work at all in this scenario. And one of the reasons is that it just works in simulation, but does not work in real world, is because it requires millions of samples to train on simulation, which is fine if you have a fast simulator. But for a real robot scenario, this might take one PhD to just run the robot once. So now, can we do something about it? Because in our scenario, the agents are exploring with curiosity. There is no external goal. There is no extrinsic objective. So why is it the case that these are so inefficient? So to address this problem, let's go a bit more into detail as to how these approaches work mathematically and can we improve them. So for instance, let me mathematically describe the idea of curiosity-driven learning, which I described earlier in just a flow chart. So the idea was as follows. What you want is you want to learn a policy that takes the image and outputs some action. And when you execute those actions in the real world, you get next image. Okay. Then I described that the way this curiosity-driven learning works is that you train a model of how the world works. So you train a model here, let's say a prediction model, which basically takes the current image and the action, and it predicts what will happen next. And this prediction is happening in some feature space. Let's not go into the detail over there, but let's say it is acting from high dimension data like images. Now the way you guide the agent to be curious over time is by computing how well does your prediction align with the ground truth. So let's say your prediction is xt plus 1, which you predict by looking at your current image in action. Then you take the error by actually acting in the real world to obtain the ground truth xt plus 1 over here. So your prediction minus ground truth becomes your error. And then you train the policy to maximize this error, to make the agent curious. But now if you think about this problem, when you compute this error, to compute the error, you actually have to act in the real world to obtain this xt plus 1. Like this robot has to move this object from here to actually see what will happen if it does that. And this environment is black box, so it's very hard to optimize for this direct objective because you cannot backprop or find gradients of this because this term here is unknown. This is coming from the environment. And that's why most of these approaches, including ours, end up relying on something on this reinforcement learning idea of reinforced operator, where you take the approximate gradient by hit and trial. Now, this is the right objective in expectation, but in practice, to estimate that expectation, it takes lots, like millions and millions of samples. And this is one of the core reasons why these algorithms are so inefficient, because they are basically trying to reinforce by acting in the world. And then if it doesn't work, they try something else, then try something else, try something else. It's basically hit and trial. Now, in our case, so this makes sense when your reward is extrinsic or reward is coming from the environment, like external goal, because then you do not have any insight, any other way to solve this problem. But in our case, the reward is intrinsic because it is coming by curiosity of the agent. So can we do something about it? Can we improve this formulation? So what we do is we look at this model over here, and instead of building one model, we say, can we somehow reduce this reward to a differentiable formulation? So what we do is we build a bunch of these models. So not just one, but a bunch of these models, which are trained jointly to minimize their respective prediction error. Okay, so this is all the same as before. But now one thing we can do is, instead of defining curiosity as the error in the prediction of the model, we can define curiosity as the disagreement in the output of these models. So the variance of these models basically becomes your curiosity reward. So now if you think about this, what all I'm saying is that you build a model, a bunch of models, all of them are trained to match their predictions, but you do not define curiosity as how much error each model has, because that error requires the ground truth value of the next state. You just say, how much do these models disagree? Now to compute the disagreement, all you need is the output of the models and no ground truth. So this is just the variance. So this disagreement basically looks like this. It is just the variance of the output of the models. So this is output minus mean and mean of that. Basic formula for variance. Now, if you notice, there is no xt plus 1 here because it does not require acting in the world. This is completely not dependent on the environment. So it's not black box. You can differentiate through it and find the answer. So it's very, very simple procedure. You learn the model and then you learn the policy through the model. So it's in a differentiable manner. And if you're really getting what I'm saying here, you might be saying, okay, this sounds similar to all these work on query by committee in active learning and model-based control, experiment design. And it is indeed kind of bringing all these ideas together. So one way to say it, it is embodied active learning. But it is done in a way that is scalable to high dimension images and does not require state space. Now, can we apply this idea in the real robot? Like, does this actually give gain to be applicable to real robot? So we look at grasping, picking and pushing kind of settings, which these prior works have done and in robot learning. But in contrast to these prior works, which use random exploration, we will perform curiosity-driven exploration on the robot. Now, before I show you the result of curiosity-driven exploration, let me show you how well does a random exploration work in this setting. So the setup is as follows. There is a robot, there's few objects, and its position control. And if I act randomly in this environment, this is how the robot performs. Now, it doesn't even touch the object for a very, very long time. Now, you might wonder, if that is the case, how come all these papers are able to use this random exploration and it still get good performance? Well, the key is that all these models, first of all, they perform two tricks. First trick that they perform is they put lots of objects at one location. And then so that if the agent acts randomly, it can still grasp or pick some of the object by mistake. And then they have a lot of these robots so as to parallelize the process. Now it's hard to afford this kind of setup in academia. So what we do is we have a single robot and few objects, but we can improve our algorithm to collect the data. So in this case, I show a result from exploration, but with this sample efficient idea. And in just 5 to 6 hours of curiosity-driven training, in few thousand samples, the robot starts to act meaningfully and collect data by picking objects, by moving them. Note that there is no goal. So this robot is purely acting out of curiosity and just collecting data, which is interesting. Now, what can we do? So far, these agents are exploring on their own, but we can take this exploration data and try to use it for solving some end task. And that procedure is very standard, which is planning. So given this task of going from input image to goal image, the only difference that I'm making is I'm learning these models from curiosity-driven data. So at a very high level, the procedure looks like as follows: that there is agent first explores the environment, it collects data, data goes into models, which are learned from high dimension input like images. And then this happens at training time. At test time, you give this agent multiple goals to achieve, and it can try to achieve those goals. So for instance, the example I showed in the very beginning of the talk, the example of tying a knot, which is very hard to solve via imitation or reinforcement learning, we try to solve it via this exploration and model building. So in the training time, agent explores, collects data, and builds model. And at test time, we ask this robot to perform any of these tasks by showing it the end image or multiple images as to how to achieve there. So for instance, let's say this task of knot tying. So a human comes and at test time, it just shows how to tie a knot by just showing it once. And this robot, without ever being trained on that example, can tie the knot by just looking human doing it once. Now note that in this setup, we do not show the whole video to the robot. We have multiple ablations where we either only show the last image or one or two images in between and apply this idea via MPC. Now this kind of framework is not specific to manipulation. You can apply to navigation, the same idea. At training time, the robot goes and explores the environment. Oops, sorry, yeah, it goes and explores the environment and it does, it collects data, which is interesting. And then at test time, you build the model and you use these models to plan for end goal. So let's say given this current image, you will ask the robot to go to this goal image, and then it can, and this is unseen environment, no map, and it can use the model to plan for this goal image. Now note that at least for navigation, you can try to hardcode this setup via shift matching or SLAM and various other approaches. But the cool part, because of which I'm showing the result here, is that this robot was never trained for this task or never even attempted to solve this task. And this behavior is purely emergent by exploration or curiosity at training time. Sometimes it might be very hard to explore everything in the world, and you might want to guide the agent via some human demonstrations or examples. So we also have some work, which I'll not go into, where we transfer these ideas by showing the robot a video of a human doing some task from third person, and we can condition the exploration or the models on that data and solve those tasks by just looking at a person from a third camera point of view. So the robot sees the person trying to do some task of pouring the things into a cup, and it tries to do it from its own perspective. And you can do the task as well. And you can. Now, one thing you must be noticing here, that the trajectories here are really, really shaky. The robot is able to do something, but it is really, really shaky. And this is a good segue into the next part. Like, what is the action space of these robots? Now, when we talked about this exploration and curiosity for robots in the game scenarios, these are just basically buttons on the keyboard. And if you look at all these papers in reinforcement learning, they do torque control, position control. But what is the right action space if you really want to transfer these ideas to the real world? So let us see what people do today in most of robot learning. So here am showing a bunch of examples of kind of the key papers in robot learning in past several years. And this is a growing community, and there are so many people working in this area where the idea is to combine the success of deep learning, etc., all these methods with robotic scenarios. Now, if you look at all these examples from the surface, they might look complex. Oh yeah, they have multiple robots, they have complex objects. But what is the catch here? What is the common part in all these images? Now, one thing, if you think about it for long enough, you will notice one thing. All of these tasks are basically handcrafted in a way such that the environment is quasi-static. So everything is quasi-static. What does that mean? Like, it means the robot can just take forever to act at each time step. Like, it can pick up something, then think for 10 minutes and then do something else. This motion is very, very robotic. And this is one of the problems when you are trying to really scale these systems to real world, where things can be very dynamic, like throwing an object or picking an object or catching an object. So let's take this task of catching. Let's say there is an arm which is trying to catch a ball. Now this task is very dynamic. The robot has to really move swiftly and smoothly to intercept the ball and to reason directly in the trajectory space. A robot which is acting about joint angles or torque at each time step independently cannot really solve this task very efficiently. Furthermore, since this is a physical system, it's no longer a video game where you can just have an agent or Mario just jump around and do something. Unlike games, these robots need to consider momentum and forces about its own body and the weights of the other objects that it's trying to catch. So what you really need in an action space or the policies is to reason jointly about kinematics plus dynamics of these robots. This is in contrast to current methods in robot learning, which basically reason individually at each time step. I already mentioned that because they are acting in this raw actions like torque, joint angles, and the motion of these robots is very, very roboticsy, like they move in a very discrete fashion. So the question is, can we build these policies that directly reason in the trajectory space? So this is one of the areas which we are really interested in, and we have an upcoming work in this NeurIPS led by one of my students, Shikhar, which is called Neural Dynamic Policies. And here the idea is that we want to build policies that directly reason in the trajectory space. And here we take inspiration from how we define motion in the natural world, like which is one of the most common ways is using this dynamical systems, which is a pair of second order differential equations, which are used to describe various phenomena in nature, like fluids, heat, motion of planets around the sun. So the key idea is, can we use the same formulation that describes how planets revolve around the sun to also describe how robots should move? And in fact, people have thought about this formulation because this is very, very natural formulation to describe real world macrophysics. And there are a line of work on defining these movement primitives, beginning from this paper from Stephen Schall, which define this as second order differential equation, and have been applied to all these cool tasks of table tennis playing, pancake flipping, letter writing. And note, all of these are very dynamic tasks. Unlike the task I showed in the beginning, where there is pickup and place and pushing, over here, the robot has to act in a very prompt manner at each time step, right? So these DMP or motion primitive based methods from control, they can handle dynamic tasks really well, and they can reason the trajectory space because they are reasoning in this differential equation space. But they also have some flaws. For instance, they require a lot of tuning, right? I'm sure some of you at least have worked with these methods, DMPs or RMPs. It's not an easy job to train them, to tune them. It really requires a full-time person working for months to get one DMP thing working. And, and furthermore, they require dense supervision like demonstrations or something else. And it's very hard to scale them to higher dimensional input. In contrast, these deep learning methods, no matter how much I diss them, they have some advantages. Like they can scale to high dimension input like images really, really well. Like images versus state is not that much different. And they can learn from weak supervision like rewards, which is given at the very end and does not always require expert data. But again, there is each time step, so they're not dynamic. And yeah, so they're not dynamic and they do not reason the trajectory space. So can we build the gap between these two paradigms to basically reformulate the action space of an agent? So like usually what we have in a deep RL or imitation learning setups is that we have an input image, which can be state or image. There is a policy, there is an action, which goes in the environment and gives a reward back. Now, instead of having a black box neural network policy, can we replace this in a learned manner or end-to-end differentiable manner with a dynamical system? So this is what basically we propose in this work, which is called neural dynamic policies, where the network outputs the parameters of our dynamical systems directly. So it has two main things. One is the goal. Where do you want the trajectory to go? Like so now this model is directly acting in the trajectory space. So you want to reason about where to go, which is the goal position, and you want to reason about how to go there, like in what shape. Should I go like this or like that? Or what shape, what is the trajectory that I should follow? And these trajectories are basically modeled by a radial basis function as in DMPs. And then the network outputs these parameters, you integrate it to compute the trajectory, and this trajectory is then applied on the environment to act, and then you can get a reward and state and train this end to end. So what we do in this paper is basically make this procedure end to end and train it via rewards or imitation in any setup that you would like, and also from images. So at a very high level, the intuition is as follows. So let's say there is a starting position and there is some goal position. Now, if I train my policies via RL or imitation learning, the policy in real robot somewhat looks like this, like very, very jerky, as I showed in the results before. It does the task, but it's very, very jerky and not very practical. But if you train it with this structure of dynamical system, you get a very smooth trajectory which respects the dynamics as well as kinematics of the robot. And furthermore, this setup is very easy to integrate in any existing algorithm. It's just like 10 lines of code that you can put in and it just works out of the box. So in the interest of time, I'll just quickly go over some of the results. So we showed results in reinforcement learning as well as imitation learning, and we get some good gain when the tasks are dynamic. So yeah, it just works, it's better, blah, blah, blah. And the trajectories look very smooth. So the results right now are in simulation, but as I speak, we are working on transferring it to real world. And we also apply it from high dimension images, but for that, please check out the paper. Okay, so far I talked about generalization in action space to new things, but what about this last bit is generalization across robots? Can we also think of generalization not only for one agent and doing curiosity and transferring to different tasks like tying knot or making rope into different shapes? Can we also transfer these policies across robot? Because every robot is different. And in fact, nobody would understand this better than we people at Robotics Institute, because all of our lab, every professor has a different kind of robot, and everyone trains their robot completely from scratch. And as we have seen in learning approaches for robotics, it's really hard to generalize them, even for minor changes in the robot. Like if I take this robot and remove the leg of the robot, it just completely fails to generalize. And there are prior attempts which have tried to address this problem, but they are very, very limited in what variations you can allow in the robot. This is one of the works which we just published at ICML, where our goal is basically to train a policy not across 1, 2 robot or a bunch of these robots, and then at test time, generalize to a bunch of new robots. And again, this is very challenging because you have different action space and every robot requires different behavior to solve this task. And I'll not go into the detail of the approach too much, but the general idea is as follows, that instead of training a policy at the level of the full body of the robot, we want to train policies for each motor and share them across all the robots as possible. And this idea, since you're training the policy across all the motors of the robot, you do want these policies to talk to each other in some manner. And we allow some ways to message pass or communicate between these robots. And so each policy each motor has a policy of its own, and these policies can talk to each other via message passing, and this message passing is learned over time. Now, let me just quickly show some results with this kind of approach. So by just sharing the policies across motors and learning these messages, we are able to train policies that can, first of all, learn and function across a diverse variety of robots. Like you can see, if a robot has 2 legs, the same policy walks. If it has 1 leg, the same policy hops. Again, across different robots, if you have a single limb, it just hops. Otherwise, it shows a different gait. Now, this I believe is an impressive results more from a control point of view, because a single controller is controlling 50 of these robots. Each robot has at least 10 motors, so it's an at least 500 dimensional control that this controller is learning simultaneously. And of course, it's not fully 500 dimension because these are different robots, but a single policy is controlling a very, very high action space, so to speak, in these scenarios. And these robots have a very different shapes, and for each different shape, it shows a different behavior. In fact, at test time, I can just take this policy and I directly transfer it to a very different robots of very different shapes. And the same controller, which was trained on something very, very different, like I showed before, it is able to transfer to some extent to all these new robots. So it does not excel, it does not run as it should be like in before, but it does a very decent job. So for instance, if you look at this robot, it discovers a new gate at test time. If you give it very heavy hands, it has never seen something like this at training time. It tries to use its knees to move forward. It has 4 legs, it is doing something else. But anyway, as you can see, this is a good initialization for fine tuning as a transfer to a new robot at test time. Again, these are robots with objects. Nothing was seen as, like I said, training time. It can still function and balance itself. We went a bit more crazy and really tried really, really different things. Like over here, there is a robot whose weight at each limb is very high, but it just learns to fall over because it just cannot do anything. This last one has no legs, so it tries to use its hands, but completely fails to solve the task. Okay, so I'll skip this part and go and cover some of the ideas, like, is it even possible to scale these robot transfer ideas to the real world? And in fact, I would say in the real world, we already have a lot of work on modular robots. In fact, Howie Choset's lab at CMU, I didn't show a figure because you're all familiar with that. And in addition to that, Mark Yim at UPenn, Daniel at MIT. So Daniel at MIT, these people already have robots that are modular. But what the results we are showing here are more from a software perspective. And so like in this case, the robot is controlled by a person manually. And over here, the policy, in our case, the policy is learned automatically to control these robots. And some of our ongoing attempts in this direction are also actually leveraging this Daisy robot from Howie this was work at Facebook. And this robot has shared motor at all locations. Now, it's not a requirement for the method for the motor to be shared, because the results I showed were across humanoid, walker, which have very different motors, and it still did okay, but it's much easier if you have the shared motors in these scenarios. So we can actually make some of these robots walk. Now, these approaches are not completely modular as in the simulation, but they are modular in terms of hierarchical system. Okay, so this was simulation across robot. Now, before I end my talk, let me talk about some of the ongoing directions that I'm really excited about, and they are not public yet. So you might have many questions as to, and I'm not showing many details. So feel free to ask me later on the email about some of these ideas. Now, if you really want to scale these systems to real robot, these three questions are not the only ones which are the hurdles on the way. There are many other. So one thing is, a lot of the learning in these systems was happening in simulation. Do I have to learn from scratch in the real world? Can I transfer from sim to real easily? Now, there is a lot of work in learning in trying to transfer this via domain randomization and other things. But everyone knows that most of these approaches basically rely on engineering behind the scene. So a person has to really construct a simulation which is transferable to real world. And one of the works which we are working on, or isn't just in submission, is how can we take the engineering out of this sim to real transfer? So we call this auto-tuning sim to real transfer. So for instance, here is an example, like you train this robot in simulation via something on the left, via with all these variations. When you try this on the robot, it does not succeed out of the box unless you really engineer the system. But with our approach, uh, we automatically adapt the simulator over time by only looking at the images, no AR text, nothing. And as the training goes, the simulator becomes close to real world automatically, and the policies transfer to the real scenario. So for instance, this was towards the end of simulator, this starts to transfer without any training in the real world. It's completely adapting with the real world data. Similarly, for this task of cabinet opening, you can the algorithm adapts over time and transfers to realistic scenarios. So one of the other direction that I've been really interested in is, so much of the work I presented today is learning from images. But as I mentioned, these images are mostly 2D images, but our real world is 3D. So can we somehow incorporate this idea of 3D perception into the learning pipeline? So this is some direction which I've been looking more on the computer vision side to see how far can we go in trying to get 3D out of 2D images as easily as possible. But if you're a computer vision person, you would see that there are so many ways people represent 3D, like point cloud, voxel, meshes, multi-views, etc., etc. But most of these representations are volumetric in nature. Now, this volumetric representation is good if your end goal is getting 3D out of image for graphics purposes. But if you're a robotics person, having a volumetric representation is just too heavy because you are trying to maintain this 3-dimensional memory, which is updating over time in the action space. It just becomes 4-dimensional and it's really, really inefficient. So one of the questions which we have been looking at recently from a vision aspect, can we somehow learn 3D reasoning by just looking at 2D images and by just describing the scene with a 2D manifold? Now, this is the last project I'm mentioning, and I'll not go into the details at all, but just show pretty pictures to end the talk. The task here is that given the input view, you want to generate novel views. So given this view, you want to generate novel views. And in order to solve this task, what you really need to do is to understand 3D, how does this world behave in 3D? So our key idea, which is a work in submission just now, is that we want to wrap the world in a sheet. So what does that mean? So I have an input image and I start with a sheet of paper like tin foil or shrink wrap, something like that. And I predict an intermediate depth representation and I predict the deformations on that sheet and I fit it onto the scene such that this shrink wrap is consistent with the depth depth prediction learned by the model. And then I use it to generate novel views. And this pipeline is trained in end-to-end manner altogether. But let me just show you the results and not talk about the approach a lot. So this is just the end of the talk, and I'll just end on these pictures. So for instance, what we do is that given this image over here, like this is the input image, no other information at test time, nothing else. And we can generate new views as if it was a 3D environment. So we have an input image, we fit a shrink wrap sheet onto the scene, then we can just walk into the input image. As if it was a 3D environment or 3D scene, we can just walk around, we can navigate. And this kind of idea applies to not just outdoor scenes like this, but also indoor scenes. So input image, you wrap a sheet around the world. Now you can actually navigate and generate novel views completely from a single image. So note that this information is coming directly from a single image at test time. So no stereo, nothing. Again, the input image, you fit a, input image, you fit a sheet around the image, then you can basically convert this input image into 3D and walk around in this image. Yeah, so you can really generate very far away views from this. And this actually, this image is borrowed from 2005 paper from Derek Hoem, which represent the scene as planes, but over here they're doing it with sheets. This also works on indoor images of objects, like again, the same story, take a sheet, wrap around the scene, and now you get to experience this image in 3D and go around and do interesting things. It's completely from single image. In fact, we also generalize it to paintings. So here is a painting. Again, we wrap the sheet around the painting, and then it allows us to navigate in the painting space. So basically, we 3Dify this painting, you can go inside. Yeah, so this work right now is mostly in the, again, one more painting in the vision domain, but we are working on transferring these ideas to robotics as well. Again, this make it 3D. It has some failures though, like for instance, this scene over here. Over here, this 3D scene is really hard because there is trees, leaves, and then there is a faraway background. So depth is really discontinuous. So in this case, if you go really close to the tree, it starts to do some blurring of the scene. Or yeah, and it works in this one more failure example where, okay, never mind. Anyway, so just to summarize the talk, what I talked about today, we talked about multiple directions to scale these ideas of curiosity-driven learning to real robot, or in general, learning-driven approaches to real robotic scenarios. First was learning efficiently in the real world. Second was how do you learn a trajectory-based action space. Third was learning policies for each motor of the robots to generalize across scenarios. And third was, and fifth and future directions were more like how do you transfer these from sim to real automatically and learn to perceive 3D from single images for natural scenes. Some of these are, I would say, very super early directions, like we are barely scratching the surface, but I still believe there's a long way to go, but the results are promising. So I'm quite excited about all this. And all the code is available except for the last few papers, which are not public yet. But I'm happy to share more details if you ask over email. Thank you.
So let's thank our speaker. We'll just clap at home. And I'm not sure how to organize the questions. Let's just try people blurting them out and hoping for the best. If not, I'll ask someone to do the raise hand thing.
One thing that I found really cool was the last thing where you're re-rendering things. And I was wondering if you had considered applying the paper from DeepMind a few years ago, generative query network.
Well, we haven't applied this yet, but other people have applied this, and they see very clear issues. So first issue is that paper was training and testing on similar environments, like similar scene, right? So you have a simulator, you go around and train with multiple images, and then you can imagine in the same scene. And over here, we are really transferring it to very out of domain images. So it's very hard for that kind of approach to work. But the fundamental difference is the scene representation network is basically a black box network. So you just basically, the way you are trying to solve the problem of view synthesis in that domain is basically hoping that deep learning will work. But in this work, we are actually employing geometry and learning together to make it work. So it's not relying on hopeful generalization. So but yeah, I think the results I was showing are very far off from what are the abilities of that model. That barely works in simulation. And I think some of the work from Katrina's lab also shows that it doesn't even work in simulation very well. So we were not quite motivated to try it, but we compare it to other approaches that shows.
Thanks. That makes a lot of sense. Yeah.
Hi, Professor. I have a question about the generalization to different robots paper. Like, I wonder, is there any intuition on what messages are being passed across different parts of the robot? And given a new robot, is there any guarantee, like in what situations these local controllers can generalize and in what situations they won't?
Yeah, actually, this is a very good question. I skipped this part, but I can quickly show to give you an answer. So what we do is we actually visualized. First point is the fact that these local controllers can control very different robots says that this coordination must be emerging somewhere. But can we really visualize what is happening with the messages? So what we did was we visualized the message of the root node, because this is a tree and there's a root node, you can assume. So we visualize how much the message varies across an episode and how does it vary. So the y-axis is 1D projection of the message, which is 64 dimensional. And the x-axis is the variation across episode. Now, in the beginning of the training, as you could imagine, that since these policies are learning from scratch, they do not have any prior as to what messages should be, and they are just random messages, so they just looks 0. So the top row I am showing is for Walker agent. This is for Hopper. So as you ask for 2 agents, but as the training goes, these messages start to take this shape, some structure. And towards the end of the training, like they take a very structured shape. So for Walker, it takes a sinusoidal wave. For Hopper, it takes 3 shapes. And for Walker, when you find the correspondence, we found that
hi, Professor, I think you're not sharing the screen.
Oh, wait, I'm not sharing this. Okay, you should have said it earlier. Okay, so sorry. Okay. Okay. So bummer. Okay. Need to share it again. I'm sharing your screen. Okay. Okay. So let me just say it easily, quickly here. So you're visualizing the variation of messages across an episode. The y-axis is 1D projection of the messages. X-axis is the variation across an episode. In the beginning of the training, messages are completely 0 because they are being learned from scratch. There is nothing interesting in them. If you visualize them, this is for Walker, this is for Hopper. But as the training goes away, these messages start to take some structure. So each plot is showing the variation across an episode over training. And towards the end of the training, they take a very structured shape. So for Walker, it takes 2 peaks where the top peak corresponds to this pose, the bottom one corresponds to this one. For Hopper, it corresponds to these 3 poses. So in some ways, these messages basically start learning internal clock for the robot as to when they're walking. And this result actually is not very, it's cool that it is emerging from scratch, but it's not very surprising for locomotion at least, because there is work on CPGs, central pattern generators, where people hard code a bunch of sine waves and cos waves to fit locomotion pattern. The only difference is in this case, these patterns are emerging from scratch. But we are also applying these ideas to manipulation, which is in the work. Over there, these patterns don't happen very naturally because it's hard to represent hand movement via sine wave. But at least in the locomotion scenario, which I showed results for, these messages take a very meaningful shape, which someone can analyze. But we don't have any guarantees, so to say, in these things. At least I don't know how to prove guarantees. I don't work in that area, but if someone is interested, I'm happy to share insights.
I see. Thank you.
Hey, Deepak. Thanks for the talk. I had a question about the tasks that you evaluate on in this one policy to control them all paper. So you're evaluating on this suite of tasks where your goal is to maximize movement in some particular direction. And you can make the argument that anything you do that gets you in that direction is giving you some positive reward. Do you think that if you were to try this modular control on more directed tasks where there's a specific goal state that you need to achieve, and more generally when you switch to tasks like this, even outside of the modularity framework, that do you think you can still expect things to work as well, or like does it just break down?
This is one of the ideas which I'm working on right now, and we already have some progress in this. So one change that we make is that instead of model free, we apply the same idea for model based setups. And in fact, we see same kind of improvement. It's still ongoing. So I would not say that we have results as good as this paper, but we are applying it for manipulation where the goal is given to achieve some task. So note that, and the reason I think this is not a surprising fact, because this approach has nothing to do with the reward function or anything. It's basically a drop-in replacement for how people do RL or learning-based robotics today. So all you are doing is you are modifying. This is a consistent theme across all the work. We take a black box policy, we open the black box, and we make it somewhat interpretable or some meaningful structure inside that. So it's not dependent directly on the reward. So one thing you could do is also apply curiosity, etc., on top of it, which I haven't done yet, but something on our horizon. But the consistency across papers is the similar. Like you open the policy, it's a blank. Like people train deep learning black box policy. We open it and we put modularity inside it. We put a sheet and mesh structure to generate novel views inside it. We open it and put the structure of dynamical systems to make it more dynamic. So all these papers are basically following the same theme in some ways.
Okay, thanks.
Any other questions?
So when you do the sheet on the object,
yeah,
I'm just a little curious as to how you do that. In other words, are you dropping a sheet and have some notion of distance and you're minimizing error or something? But you can't do that because you don't know the distances because it's a 2D image you're starting with.
Oh, yes, yes. Okay. So, so there are two phases. I went very fast. So at the way you train this system is by having access to two images. So from two different views. So you train it by that. At test time, you only have one image. Okay. So so basically, what is happening? So this sheet thing is here. Okay. So at training time, you have two images. So you have an image from this view and some target view, let's say. The way you train this is that you take a sheet, you generate some deformation for the sheet, and also what is the depth of each point in the scene. And then you fit the sheet onto the scene like that, like a mesh. Then you can use geometry to render the sheet from different point of views. And then you get a target view. Like let's say you had a pair of input view, target view, and the camera transformation between them. You train on this completely end to end. Then at test time, all you have is just a single view, and you can pass arbitrary cameras to generate it from different views. So one question is, if you naively fit a sheet onto an image, there is a trivial solution, and the trivial solution is that a sheet should basically fit the whole image as a plane and not really capture the 3D part of it. But we avoid that trivial solution because we are also predicting an intermediate depth representation, as well as we are training from a target view, which is not the same as input view. But there is no other supervision at training time, except for 2 images, which kind of prevents this trivial solution.
Okay, thank you.
Yeah, at test time, you only have a single image.
So does anyone else have any more questions?
Hi, Professor Pathak, I have one quick question. Just kind of a follow-up to that one. You mentioned you generate the different deformations. I was just curious, like, how do you generate the different deformations? And is that kind of how you help it generalize across the different
Yes, these deformations are basically, so it's basically learned via gradient descent, right? So this that the fact that what makes this work is that this whole pipeline is end-to-end differentiable. And there are multiple components to it. There is differentiable rendering, and this is a novel differentiable texture sampling. So deformations are basically 3 things. For each vertex in the mesh, you predict how much to deform it in the spatial direction and how much to deform it in the depth direction. And then you predict this deformation for all the vertices. You fit a mesh, you render it from a novel view, you take loss. And the hope is by doing this at training time, since you're training this over multiple pairs of images, it will learn the structure that if there is a wall, it should be a single flat mesh. If there is a floor, it should be a single flat mesh. But if there is an object, I should really wrap around the object very nicely to get good new views. So it's basically because of learning at training time. Does it answer your question? So it's a latent.
I think, yeah, that answered my question. Thank you.
Okay, well, again, let's thank our speaker. Also, we wish you all a good holiday break. And just everyone, I hope you stay safe. Thank you, Deepak.
Thank you.
That was a great talk. Thanks.